Good afternoon, everyone. Welcome. Today, we're happy to have Dr. Cengiz Öztireli from University of Cambridge. Cengiz is actually a graduate of Koç. He did his undergraduate here, double majoring in computer science and electronics engineering. He then moved to ETH Zurich for his master's and PhD work. He works, I believe, with Marcus Gross, and he's got a number of high quality, high impact publications. He is currently an associate professor at the University of Cambridge and a senior researcher at Google. Before moving to Cambridge, he was a research scientist at Disney Research, and he was a senior research associate at ETH Zurich. His general area of work is in computer graphics, 3D modeling, but he also has some work in my main area of interest as well. He did some work in sketch-based modeling, sketch-based interfaces, and he's also one of the co-organizers of the CVPR workshop on deep sketch recognition. So without further delay, I'd like to give the stage to Cengiz, and thank you in advance for being with us today.
Thank you very much for having me, and also for the nice introduction. Actually, so yeah, I mean, I'm a graduate of Koç in 2006, so it's been some time, and today I'm pretty excited. Actually, I mean, obviously, I've been giving a lot of talks around the world, but for this talk, I'm in particular excited. I feel the excitement, I think, like after all those years being at Koç. And today, basically, I'll be talking a bit about our efforts on creating a form of 3D digital reality, essentially over the last 10-15 years. So my background is in computer graphics. Then I switched to computer vision a bit after my PhD, and then to machine learning. So basically, it's kind of a combination of all these. And the main idea is that if you can create a form of 3D digital reality that's actually suitable for machine perception, then we can allow everybody to have a form of 3D digital reality for themselves without requiring all the big setups and all the industry. We have all the research setups we have at the universities. So ideally, from a cell phone or maybe some mobile devices, hopefully at some point we will reach a point where we can capture the visual world around us and ourselves. So this is the main goal. And actually, I worked, as you mentioned, in the past in companies where creating 3D digital reality was actually done by professionals. Let me see if this advances. So hopefully you can see my slides well. So in particular, I worked at Disney for 3 years, and there actually I experienced how difficult it is to create reality firsthand. So for Disney, actually, there were almost 1,000 people in a studio, in a particular studio. And these were all talented people who were working for a lot of hours per day. And with quite cumbersome tools, of course, like they've been working with these tools for a while, so they're really proficient in these tools. And still, it was really difficult for them to create a form of 3D digital reality with all the intricate details. So, I mean, this is of course not feasible for all of us. This is more like for companies or maybe some labs access to such talent and computational resources. And if you want an alternative way of getting 3D digital reality, is basically via capture. I don't know why this is not advancing well. Okay, so capture setups are of course also there. So it's actually particular images from this so-called light stage. So in the light stage, you have actually well-calibrated lights and cameras. And the idea is you can then put an object, for example, a human face, and you can capture the geometry and appearance of the object. But of course, as you might imagine, the light stages are also pretty expensive. and also you cannot just have it in your living room. So I mean, this is a viable option if you run a production studio or some large lab, but typically this is not also something that we can easily deploy, especially for mobile capture, so that we can actually allow everybody to have a form of 3D digital reality for themselves. So at the moment, there are these two basically different ways, fundamental ways. So one is creation, which is kind of the traditional way, and one is capture, which has been advancing in the last decades. And now we have quite nice systems, but not really suitable for everybody and everyday use, basically. So the main goal of my research is, can we have a system and a form of 3D digital realities such that we can allow everybody actually to have it for all purposes, including everyday usage and also for professional purposes. So before going into details, I wanted to give you an overview of how I see the field at the moment, because as I mentioned, it's actually now a merge of quite different fields that kind of come together over basically some common concepts. And of course, everything starts since we work with computers with digital models. So we have models of geometry, appearance, lighting, etc. And as I mentioned, actually, this like the typical way to get the models and the parameters of the models is basically by people. So creatives or like people like us, or actually typical artists, they author the models or the parameters of them. And all these models, of course, are models of reality. And from the models via rendering, or from reality via sensing, then we can go to projections. So here I'm actually using projection in a general sense. Could be a depth map, could be an image. So it's basically a partial view of reality. And then finally, from projections to models, we can use perception algorithms, machine perception, to basically go from projections to models. So this is kind of the summary of what I've been working on. And in particular, these four areas are what I've been working on quite a bit in the last 10 to 15 years. So I worked a lot on developing the relevant models for different parts of 3D digital reality and how we render them to go to projections, and also how we basically go back from projections to models. And in this sphere, actually, one big idea that I've always worked on, and what I've also just described in this talk, is basically defining machine perception as almost like an inverse process. So the idea is if you can actually model each aspect of 3D digital reality carefully. So for example, geometry, lighting, motion, cameras, appearance, and some scene semantics as well. So if you can model each of these, and actually, if you can also have a machine learnable rendering process so that you can go from a scene definition to an image, then you can also define the inverse process. Basically, you can go projections back to the parameters of these models that you've defined. So this is actually the whole idea. And I'll be just talking about the different boxes here, and also some applications, so that hopefully it will give you an idea of how and why we do this. But before that, I just wanted to, of course, thank first and foremost my students and all the excellent collaborators and all the support we got from both industry and academia over the years. Yes, it has been great. I mean, I always enjoy working with a diversity of people, and all these projects are, of course, collaborations. So before going into a couple of these boxes, as I mentioned, I wanted to briefly talk about a particular application. It's actually 3D capture, especially capturing human bodies and objects related to human bodies. And of course, when you talk about human bodies, the first object is pretty much quite important, is hands, and the other one is faces. So I wanted to just basically give you an idea of how these systems look like by talking a bit about hand capture, hand pose estimation in particular. So that you will understand how these components come together and why it makes sense, basically, to have these different models for different components. So for this particular example, let's assume we actually start with a depth map. So we have a depth map that comes from a hand. And now we can actually run, of course, some neural network to estimate pose parameters. So if you have the right supervision, if you have the depth map and the corresponding ground truth pose parameters that are accurate, then you can do this. And you could stop here for some applications, but typically it doesn't work so well. I mean, there are multiple reasons. So one, the pose estimator, typically you assume it's a generic network. And I mean, there are certain architectures to use, but you don't really get to the system's prior information that this is actually a hand and you want to actually get out some pose. So you have no prior information at the moment here that you actually input to your algorithm. So instead of this, what we do is basically we say, okay, we have the pose from the pose parameters, but we can also have the shape, for example, in the form of a point cloud. So in this case, we have a hand shape. And then what you could do is basically use the pose parameters and the shape to deform the shape into the corresponding pose. And then you can actually render this. For this example, I'm just using a simple differentiable render. It's just a resample and rasterizer. So we can actually get the depth map out of this. And then you can do the same process for the input depth map we have. So that actually these two depth maps, we get a comparable. And then you basically compare and backpropagate the error all the way back to the pose estimated parameters that you have. So the system works pretty well. And also, as you see, we actually almost get sub-supervision in this case because we started with a depth map and also basically some architecture that encodes all the inductive biases we have. And in the end, we didn't have to actually use ground truth pose parameters in this case. And the other good thing about such systems is actually, since you modeled each of these components individually and carefully, you can also impose constraints on these components. For example, for the pose, we know that, so this is a physical human hand. So for example, the fingers cannot bend backwards. We cannot have interpenetrations of the hand. You can also explicitly impose these constraints, which of course also conditions the system quite nicely. So that basically you don't get supervision like in the forms of all these parameters, but you also but you still get a quite robust system in this case for hand pose estimation. Now this was from depth map, but you can imagine extending it to actually an input where at training time you get both the depth map and the corresponding color image, and at testing time you just have the color image. So you can easily extend to this system. I just wanted to highlight basically that you can have different versions of the same system quite easily in this case, and in most of the cases for 3D capture. So in this case, it's the same. So we start with, in this case, a color image, and we have a pose estimate. But we don't directly actually try to estimate the pose parameters, but we have a latent space. And this latent space implicitly captures, so we pre-train this latent space, it implicitly captures all the constraints due to the physics of a hand. So due to the fact that this is actually a human hand and we have some physical constraints on it. So from the latent space, then you can go to the pose parameters, and basically the rest of the system stays the same. So you still have a shape, you deform the shape, you have a differentiable render, in this case a simple resample rasterizer, and you get out of a depth map. Now you can do the same for like apply the same process for the input depth map, and basically you pretty much use the same system, except in this case you have just input color image and the corresponding depth map at training time, and only the color image actually at test time. So now we extended the system also to work with color images, and the only difference we have here is basically this pre-trained latent space, which is also some idea I use quite often. So instead of explicitly imposing constraints in the form of losses or some other architectural constraints, it's always possible to kind of pre-encode these into latent spaces via pre-training some of the networks before you start the actual end-to-end training. So yeah, actually we applied the system to a couple of different problems. For hand tracking, it works pretty well. Of course, I mean, there are always problems with occlusions if you have too much occlusion, or if you have a hand shape that's really different than the hand shapes that you trained on, trained the algorithm on, then it can fail in certain cases. But especially for gesture recognition, it worked pretty well for us. And that was actually the primary reason why we developed this algorithm. Of course, also then we use it for hand tracking as well. But especially for gesture recognition, it also was working pretty well for different hand shapes and different lighting conditions, etc. Although we trained on a combination of synthetic and real data with certain hand shapes, we didn't have too many hand shapes in this case. And a similar system or similar ideas, actually, you can easily apply to, of course, capture different parts of your body or different objects. So, for example, we used quite similar idea to capture human body shapes from a single image. And then we also applied it to a bit more exotic objects, such as garments. And one reason I wanted to highlight this particular garment shape estimation project is actually, we didn't have any real data in this case. I mean, this is also one big problem, of course, typically. If you want to capture objects with all the intricate details, and the capture system you have does not really allow that. I mean, the only thing that you can do basically is resort to synthetic data. And for this particular project also, we synthesized actually millions of shores, is basically simulated, and then photorealistic rendered them to get our ground truth data set. And then we can basically have some success on capturing the garment shapes, which are of course really difficult to capture with all the intricate details due to the wrinkles and some of the deformations. So I did work well as well. And then of course there are so many applications of the shape estimation and capture. Sorry?
Sure. Can I ask a question about your models? Your model of the hand and this human body, do you have like just a volumetric model, a skin model, a mesh model, or like a skeleton model? What do you have?
It's actually for the garment shape, it's just a mesh. For the hand, we have for that project, actually, we had two different models. So one is more like a PCA type, so basically like a plant shape type, and the other one was a skeletal one. So it's basically some lens scaling applied to the hand, and we define a certain topology for the skeleton and fix that. So we just estimate the joint angles essentially, and then we can map these joint angles basically to the mesh using linear lens scaling. So this is what we did.
Okay, thank you.
So when you say mesh, is it surface mesh or volume mesh?
It's a surface mesh.
Surface mesh, okay.
Exactly. And more recently, actually, I've been working on this neural volumetric representations, which are more like also capturing the internal structures. It actually works a bit better for certain cases, especially if the topology is changing. But for this case, actually, since the topology is fixed and we don't really get interpenetrations, surface mesh for our purpose was actually sufficient. So yeah, of course, 3D capture is a lot of applications, but I just wanted to highlight one particular application. It's actually a collaboration with the company Vizati, and the idea here is you actually interpolate video. So you have some cameras in the game here, and you just have the fly-throughs from one camera to the other. So you interpolate. Of course, you don't typically stop in between because it's a bit blurry as you interpolate, but you can have these nice fly-throughs. And basically, before they were using simplified models for the players, almost like a rectangle. And then we said, okay, actually, what we can capture the player shapes, and basically you use it especially for close-up shots, because if you just have almost like a billboard, when you interpolate views, it doesn't look very realistic. But with, of course, a full 3D shape, it's much better. So this is, I think, one interesting application. But obviously there are now new applications in AR, VR, and image editing, image relighting, and 3D printing as well. So yeah, it's actually one big application, obviously, of what we've been doing over the years. So I wanted to first highlight that. And now I want to go also a bit in detail on this component. So I mentioned differentiable or machine learning rendering. I mentioned geometry representations and some other boxes like lighting, appearance, etc. So I'm not going to all of those, but I'll talk about rendering and geometry essentially, and then also some machine learning techniques we use to actually make those techniques work well. So I want to start with the rendering, and of course, since I have a graphics background, I'm actually well versed in the rendering. So obviously, we know that for a lot of decades now, we know how to photorealistically render scenes. But the type of rendering I'll be talking about is actually not general graphics rendering. It's actually a specific type. It's with these three main properties. So the first one is our rendering algorithm should be obviously machine learnable, meaning most of the time differentiable. And this is typically the main problem actually. And then the other big problem is efficiency, obviously. Typically especially for production level renderers, they're pretty slow. And you can have rasterization based ones, like more like OpenGL type, but then you don't really get global illumination effects, and some effects are really important for getting realistic scenes. So efficiency is always a problem, and even for rasterization, actually, it's not really just easy to just plug in some rasterizer and basically train your algorithm, because first it's not differentiable, so you have to somehow make it differentiable, but also typically the level of efficiency we talk about is actually is not the same as the efficiency we talk about when you say OpenGL and real-time graphics. So for example, real-time graphics, you can say 60 FPS is okay, but if you really want to train a large system fast, then 60 FPS is actually not too much. And then the third property is actually typically you want to render to the task specific. So you don't expect that the same render would work for both 3D capture and appearance capture. So you need to fine tune it, basically using this full spectrum from rasterization all the way to path tracing. So I mean, what kind of effects do you want to capture? What kind of materials or geometries you're considering? Are you considering that the topology will change? Are you considering the camera is moving a lot, or the lights are changed? So basically, you typically want to specialize your renders actually more task specific for this case. So I've been working on quite a bit of differentiable renders recently over the last 2-3 years. But I wanted to highlight actually one particular one in this talk, and it's differentiable rendering of point clouds. I mean, actually, point cloud is what I started also with Çağatay Hoca at Koç as my first project. So it's also very close to my heart. And of course, point clouds are also super important. I mean, like, typically what we get out of the capture systems are in some form, either a point cloud or some other unstructured data we can convert to point clouds. And the idea here is, can we go back from images to point clouds by basically first formulating the forward process of rendering point clouds. So for this one, what we did is actually we finalized a project almost a year and a half ago now and published it. So what we did is basically took a splatter. A splatter is just an algorithm where you define around each point P a sound disk that's actually orthogonal to your surface normal. And you just project all the splats to the screen space and basically blend the contributions from the splats. And so this is just the process. And we just took that and basically made it differentiable and efficient. So this is kind of a blueprint of all these algorithms. So you take an existing render from graphics, and then you first make it differentiable and as efficient as possible. So for all these cases, the main problem always is occlusions, basically. So imagine that you have actually a splat, and at the moment at X, the splat is not right there, so it's not visible. And now, as you move the camera or as you move your geometry, it becomes visible and invisible again. So basically, then this creates the discontinuity on the image plane, right? And how do you deal with the discontinuity? This is kind of the main point of a lot of papers now. Probably there are hundreds of papers by now. And as I mentioned, I've been already working on a couple of them. So yeah, this is a big problem. How do you deal with occlusions and discontinuities in your scene? But once you somehow approximate it or smooth it out, then actually what you can do is, for example, given multiple views, you can optimize for geometries, in this case, point clouds. So this is the essential idea, making the forward process differentiable and machine learnable, so you can invert this process to get back to your scene properties, in this case, the geometry. So this was the rendering box in the pipeline. And of course, one quite important box in this pipeline is the geometry one as well. And I worked on geometry quite extensively over the years, especially for basically developing representations that are suitable for machine perception. And I think for geometry, we need to distinguish between these two cases, and especially over the last year or two, probably 3 years ago, it started. This implicit null-based geometry representations actually are becoming popular. But basically, there are two ways, right? So one is explicitly representing a geometry. It could be a mesh, could be a volumetric mesh, could be a triangle mesh, or point cloud. Or you can implicitly represent your geometry in terms of, for example, an implicit function, or some occupancy function where it's 1 inside, 0 outside. So basically, then you can learn this function. You can represent this function with neural networks and learn the parameters. So now there are just two main ways of using geometry for machine perception in the field, and implicit ones are actually gaining popularity over the years. And my first paper was actually on that. So my second paper was on implicit representations. And there already it was clear that if you're not really careful with the representation, you cannot get a faithful surface. So with implicit ones, basically, depending on what you want to preserve, in this case, for example, if you want to preserve sharp edges and corners, then you really need to fine-tune your representation according to that. Otherwise, you can easily run into problems. Actually, we recently concluded a project this year, and there the main problem was not sharp edges, but basically the topology of the surface. We realized that if you use just some of the state-of-the-art neural networks to represent your implicit surfaces, then you can easily run into topological problems. So basically, it really needs to capture these properties of the surfaces if you want to use an implicit representation. But then, typically what we get, as I mentioned, out of the systems is not an implicit one, but more like an explicit representation. And again, I wanted to give the point cloud example, since I already started talking about point clouds. Now, you can of course use your system to get some geometry, but the geometry will not be perfect. And one interesting thing about all this framework is actually you can almost invert it and use it also to further process your explicit geometries. So let's say we got a point cloud out. And what you can do is, again, using the differentiable renderer I just talked about, you can actually render it into an image. And then you can run some algorithms on the image to actually consolidate or make your geometry better, more faithful to the original geometry. So, for example, we can have actually image-based classification, and then image-based so-called consolidation, basically getting rid of the noise and resampling the geometry. And obviously, classification also helps for consolidation. If you know what kind of object actually you're working with, it really helps to process the object as well. So in the end, you can get actually a nicer 3D geometry out with the actually correct labels for its class as well. So this is the same process, and we just turned our geometry now into an image-based representation, because then we can easily run algorithms that work on images. At the moment, of course, the 3D data sets are becoming larger, but still we have much more images than 3D geometries we have. So it always makes sense to first go through images and do all the processing there for geometry still. And then the other thing is, of course, if you have convolutional neural network or some way to regularly sample your data before you process it, then it's much faster. So basically, this process actually works pretty well for both of these reasons to actually get back much better geometries than what you would normally get out of a classical capture system. So just want to give you an idea of how the systems look like. So let's assume we have a local geometry patch. In this case, it's actually a patch consisting of a bunch of points. I represented the points with disks here. And we would like to get a nice surface patch out of these points, basically. So what you do is first, you estimate the view. So it's kind of a rotation and translation almost. And then basically you can input this view, the estimated view and the point cloud into a differentiable renderer again. And in this case, we just use a super simple resample rasterizer. And then you get some form of the depth map out. Then what you can do is basically apply some algorithm, for example, a denoiser on this image. And then you can actually back project this image to 3D by using the estimated view, and you get your output surface patch. So this is the whole idea actually of geometry processing for machine perception. And then you can actually get quite nice results. For example, you can perform denoising and resampling on the input data, which could be quite noisy and not really nicely sampled. And also apply it for geometry reconstruction to get much more faithful surfaces. This is actually a result we got a couple of years ago, and I was quite amazed by this because, like on the left, what you see is this state-of-the-art detail preserving surface reconstruction. Actually, some of our previous work, and we worked on this problem for quite a bit, right? So for 10 years almost. And then a couple of years ago, we said, okay, let's use some learning. And then we immediately could get much more improved results just because we know that this is a face and we actually have access to surface patches and some other details from a face. So yeah, I was really amazed to see actually this the first time. Now, of course, this became quite normal. But at the time, it was really nice to see. And then if you look at the details, for example, on the normal maps, they also look pretty good. So we tried training on faces, testing on faces, so we could get these nice results. We tried training on, for example, garments and testing on faces, then you don't actually get those results anymore. So basically, I think there's a lot in the data that we can capture by using some of these techniques, also for geometry. And then you can use it for, of course, for real-time capture in some real-time systems as well. So this is from another project where we get quite noisy depth data from some sensor, and then you can use similar algorithms to basically get a much more faithful reconstruction. And I think an interesting application of this, and this is something I worked a bit in the past as well, is actually 3D printing. And in this particular case, actually, the idea was 3D printing works in Disney parks. And just to give a rough idea of the process, actually, it starts with carving out the shapes out of foam. So basically, you have a foam, and then the artist carves it out, and basically, then you need to scan this. And of course, when you scan them, there's a noise introduced and some other artifacts. And then you typically want to consolidate that geometry as we did. And basically, these algorithms are also super helpful in that case. So as I mentioned, you can do reconstruction, consolidation, resampling, but you can also do a bit more. For example, segmentation or classification. In this case, the algorithms are pretty much the same. Like the overall architecture is the same. You can actually view estimators as before, basically translation and rotation. And you just rotate and translate your point cloud. And then you can, again, differentiate the render your point cloud. In this case, we used, again, a simple resample rasterizer to get a depth map out. And you can use a classifier, image classifier, to basically classify multiple views. And in this case, I'm showing 2 views, but you can imagine going to n views and basically do a pooling and get your classes out. So this is the same, almost the same system. But now it also works for classification. That's something we published also a couple of years ago. And this is the output you get. Actually, we could get quite nice, quite accurate classifiers. And an interesting byproduct of this project was also, since we explicitly optimized for the views, you could actually get the most and least informative views out of this architecture. And it kind of matches human intuition. For example, for the chair, the algorithm tries to expose the X so that it's clear as the chair. And actually, these are also consistent across particular class. So basically, if you have the same class, for example, lamps, then it's always giving you the same view. So meaning that the algorithm learned to rotate and translate the object such that it will have an easier time to classify it. And I think this is one theme, this is one good thing that always appears in such systems. If you model each of these components carefully, then first you can impose constraints on them, and second, you can actually get such informative byproducts out of your system. So yeah, this is actually pretty much what I want to talk about regarding geometry. But one thing overall that's I think a bit ignored at the moment, if you want to have a scene representation for machine perception, is the sampling problem. Sometimes people explicitly tackle this, especially in graphics, of course, since, as I said, I also have graphics background. I've been tackling this problem for quite a bit. But in perception, I think now we start to realize that this is also a big problem. And if you think about it, of course, we work with computers, we have everything in a sampled form. And the way you sample structures in your system for representing your scenes is really giving you worse and better representations of reality. So, for example, if you want to render a photorealistic scene, you typically need to sample rays in path tracing or paths. If you're not careful, then you get all this noise and some of the artifacts. And if you're more careful, then you get much more improved characteristic renderings. And this goes for everything. Goes for geometries, goes for the material representations, goes for the lighting. So we need to be really careful about sampling. I think that's a bit of an overlooked problem. And one thing I've been working on to tackle the sampling problem for scene representations is basically using this theory of stochastic point processes. I'm not going into details of this, but just wanted to give you an idea why this is important and how it roughly works. I mean, this theory actually has been developed in physics and statistics for 50, 60 years now. And the main idea is pretty simple. So you have a point process. That's like kind of a process. It can be an algorithm, can be a manual process, for example, a child placing soldiers, etc. And basically the idea is this process can generate infinite many distributions with the same characteristics. So the distributions themselves are different, but they share the same characteristics. And the way it works, I'll just roughly explain, is basically assigning random variables to sets in your space. For example, let's say you fix a set B, and then you can define the random variable as a number of points that fall into this set B. And in this case, in this particular distribution of 3, if you just generate more distributions from your point processes, it can be, for example, 5, or it can be 2, then you can imagine having the distribution of these number of points that fall into B to represent a certain property of your sampling. And you can also define actually joint distributions. You can define multiple sets in your space, and basically then you have these joint probability distributions that capture correlations among samples. And this just goes like this. Like we can go higher orders as well, and then apply this to basically understand and also optimize for your samples distributed in your scene. We actually applied it to quite a bit of different structures. For example, for geometry reconstruction, if you're careful with your point placement, then you can get much nicer captures and reconstructions. The same goes actually for the recent systems. We published recently a paper. It's basically on using careful sampling, this time for a neural network-based capture system where you trace rays to render your geometry. Now we can guide your rays carefully with these samples, and you will get much more accurate reconstructions. And you can use it for different effects. For example, for motion blur, if you carefully sample time in this case, then you can get much more improved effects for the same sample count. or you can use it for modeling repetitions. Just the same theory applies basically. You can just have image pair repetitions, geometry repetitions, or sound repetitions, which are of course quite important also for capture and perception systems, because we have repetitions all around in the visual world. And you can also use it, for example, for synthesizing a bit more random structures. In this case, actually, we had a map of an artificial forest we wanted to reconstruct. And we had some examples of tree distributions from the real world. And we could just map this map to a distribution where we can render a realistic forest. And I think one very interesting application of this was via this collaboration with the company VIEWPOINT. This is a physical software. This is a medical simulation company where they want to basically simulate arthroscopic surgeries. And the idea was we could actually represent these intricate structures in the body by using again point processes. Since there's a pattern, but it's also random, we can actually capture both by using pretty much the same theory. So this is, I think, the power of using point processes for scene representations. Yeah, so finally, I want to briefly talk about some fundamental machine learning techniques that you might want to use, or you might want to improve for your particular systems. And actually, for me, it worked pretty well. I mean, as I said, my background was graphics/vision, but then I actually started to realize that so many systems, especially since 2013-14, so many systems we use they're based on neural networks, and we don't really understand how they work, which is of course a problem from a scientific perspective, but also from a practical perspective. If you don't understand, you don't know why they will fail, how they will fail. So that's why I actually started this thread of research into understanding a bit more like these machine learning algorithms we use. And the first thing, so basically there are two things I want to talk about. And the first thing is interpretability. And I think this is really fundamental. This is fundamental both now from a legal perspective. Now there are laws that says, well, you cannot have an algorithm decide in your life and you don't understand the algorithm. So basically, if a party asks you, you have to explain why the algorithm decided that way. As I said, it's also very important from a scientific perspective, but also from a practical perspective. You need to understand the algorithm to improve and to make sure that it doesn't fail the way you don't want it to fail. So interpretability is actually a big area now. I worked on this for 4 or 5 years now. We published quite a bit. And I'll just start with an example of a classifier. I think this is an easiest example to talk about when it comes to interpretability. So let's assume you want to actually classify X-ray scans. Now, the classifier in this case can give you the output as normal, so it's like a normal scan. Or it can say, well, in this case, it's abnormal. But the problem with all the systems, both classification and regression systems, is actually you don't know where it looked at. So you don't know what it actually cared about in the input. I mean, somehow in your data set, I mean, all the data sets in the world are fundamentally biased. And you cannot really have a perfect data set where it captures all the cases. And typically you have some bias built in. So for example, there could be some correlation between the abnormalities in this case and some lines that you have in the image, maybe because of your data set, maybe because of something else. And you don't know if it really overfit to this one, like the lines, or it really saw the bone itself and cared about it. And this is actually a real problem for our cases where we apply it for example, segmentation, reconstruction, etc. So let's assume we still continue with the classification example. Now we want to classify an image. So in this case, is it a snake or is it something else? And you can actually use the so-called attribution techniques to understand where the algorithm actually looked at. So an attribution technique basically takes the input, the classifier, in this case the output, and gives you almost like a heat map. Basically assigns an importance to each of the pixels in the image in this case, but you can also do the same for the internal nodes in your network, so you can understand how much each node is actually contributing to the output. You just use the same techniques basically for the input case or for the internal node case, and it gives you an important score essentially. So when we started looking into this problem, actually there have been hundreds of obviously papers already, and the first thing we did is we could actually unify some of these into a common framework so we can understand them basically. And then the second thing we did is introduce a new one based on Shapley values. So this is actually what I wanted to briefly talk about, just to give you an idea. This is actually a game theoretic concept, and I think it's really interesting how it could be applied for our case. And just quite briefly, if you are a coalition of some people, let's say you're a coalition of 3 people, the idea is you want to, and you produce something of that value. In this case, you produce a console that's actually, you can sell for $100. The idea is you want to quantify how much you contributed to this $100. And it's actually a pretty conceptually pretty simple measure. You say, I'm actually adding and removing myself to each and every subset of these people. So for example, a subset of 2 people, you add yourself, remove yourself, and take the difference. And you do it for each and every subset, and you sum up all these differences. So this is the whole idea. Now, obviously, this can be used, right, for quantifying how much each input pixel or node in the network is actually contributing to the output. It's also kind of a coalition. And this is nice because it's theoretically well-founded in game theory. It doesn't care about how you implemented it. The main problem was actually to compute is actually, it has exponential complexity. It's a combinatorial problem basically because you have all the subsets. So what we did is say, okay, how we can apply it to deep neural networks. So let's say you're given a neural network, and the fundamental idea is you say, well, I actually talk about the distribution of my subsets. So I have a certain distribution of, in this case, all subsets of pixels. And I can imagine actually passing this through layers of my network such that after each layer, I have a different kind of coalition, right? Because the coalitions change, like the input pixels are turning into some other pixels as you actually move along. So basically the distribution of the subsets also change, and you can just use this warp distributions to compute Shapley values. And we applied it to quite a bit of different problems actually beyond visual data, and for all cases it worked quite well. And the last thing I want to talk about very briefly, again, I think this is also very interesting, is actually improving convergence. This was also a big problem, of course, for us. Sometimes we were, like the algorithms were converging really slow, sometimes not converging very well. So I started looking into this problem. I just illustrated, again, with a classification problem in this case. And let's say we have 2 classes, and we have actually an actual boundary between the classes and the current boundary. What you do with neural networks and stochastic gradient descent is basically approximate the gradient. Right? The gradient is an expected value of a loss function, actually the gradient of a loss function. And what you do is you sample your space to approximate this gradient. And basically, then you can say, well, I have actually a bias and a variance for this estimator, and you can use it to really improve convergence. I think this is also a very interesting case. I mean, where we use pretty much the same point process theory, but in this case to improve the convergence of algorithms. And we again applied it beyond visual data, and it worked out pretty well. So yeah, this is actually all I wanted to talk about from the machine learning side. And I think now everything is coming nicely together. I'm quite optimistic for the future of 3D digital reality. Hopefully, in 10 years or so, we could actually already have systems that will be able to capture quite accurate and faithful representation of reality, and we will be able to also augment them with new objects, and hopefully then it will be like this new form of 3D digital reality will be available for all of us.
All right. Thank you, Cengiz. We finished right on time. We have time for questions. Thank you for the great presentation, by the way. You touched up a lot of different topics, and I'm sure everyone probably picked up 1 or 2 ideas that they would probably follow up on their own. So let's open up it for questions.
I can ask a question if nobody asking. Cengiz, it has been so long that we work on this registration problem, like when you were in undergrad. So I haven't followed up on that topic much. Like, what is new in that like registration? We work on feature-based registration, but what, like, I think later on you work on spectral methods and things like that, if I am correct. So what is new in that registration domain, like 3D registration domain?
Yeah, actually, interestingly, the ICP algorithm is still being improved. There was a paper a year ago at SIGGRAPH, actually, and basically working on the different metrics for point, surface to surface distances, and it seems to improve actually the results quite a bit. Also, there were sparse versions of ICP recently. Yeah, actually, ICP is still advancing, and for feature-based ones, now people are using deep features, basically features from neural networks. It's similar to using image features, so you can match them. Registration is still a big problem. I mean, the calibration systems, of course, they advance in the meantime, and now from multiple views, we can actually get fairly accurate initial alignments, but still there are some sensor noise, and sometimes the sensor moved a bit, etc. So they're not perfect. So in this AR systems, still registration is there, basically. And at the moment, typically, I think they're using ICP type approaches because you already have some initial alignment that's okay. But for the cases where you don't have it, for example, let's say you have like in the wild capture, you just download it from the internet. You have no idea about the calibration, and of course, feature-based ones are the norm.
We're interested in like attaching a camera to a robotic arm and trying to estimate the surface normal with a single camera. Do you know any concepts or techniques? How feasible is that? Like not stereo camera, but single small camera where it will be placed at the tip of the end effector of the robot, and as the user moves the robot around the object, we like to capture the surface normal very quickly. I know this is feasible with the stereo camera, but is it feasible with a single camera? Do you do any work along the lines of that?
Yeah, so actually what we use is IMUs, so basically just to get the calibration, so that you actually know from one frame to the other how much and how you move your camera, so you can actually use them also in almost like a multi-view system.
Mm-hmm. So maybe we should talk if you have some time, maybe in the future. We like to talk, we like to pick up your brain on that topic.
Of course, it would be great. I will be happy.
Okay. Other questions? Maybe I can ask one. So you talked about using data generation for kind of constraining your models in a way, creating inductive bias, right? You use this computer graphics pipeline in a way to help you with the vision, the perception part. And you talked about constraining your model, you talked about inductive bias. I was curious, and you talked about differentiable models as well. I was curious about to what degree do you enter these inductive bias like information or the constraints through the generation of your training data? To what extent are they directly plugged into your networks through renderers or inverse renderers? So that's been kind of bugging my brain as you were talking about these.
Exactly. So for that particular project, the government one, we actually just use it as data. But these days, actually, we're building models out of them, and then basically using the models in our architectures. For example, if you want to work with faces, you can actually scan faces, and then you can build a model of faces. Of course, then you're fundamentally constrained by the data that you have, but you can then synthesize more data and basically add it into the mix, and then you have an expanded model, and then you can actually use that model to, for example, run the parameters of it, or actually you can use it to constrain or to condition your system. For example, you can say, well, I want to be close to the space of these models that I have. So you kind of have a pulls your algorithm towards that space. So you're not on that space, but you're close to the space. So yeah, we're using also now this kind of ideas. But yeah, for that particular actually one, we just use it as a data set. One other idea that I'm really fond of is actually coupling this together. So basically, at the moment, in industry and in academia, typically the data generation part or the synthesis part is really decoupled, most of the time decoupled from the actual perception system. But we know from neural network literature that adversarial training is really important. And I think it really needs to be explored. So basically, going back from the perception system and informing your capture or synthesis pipeline, okay, saying that, okay, I need more data in this part of the space, for example. Now it's not there at the moment. So that's why I think the data synthesis or generation systems are not really doing like the most efficient job. They just, put it like just outputting it over data, and then we hope that it will work for our case. But I think we can really tight a couple of these more.
So maybe an equivalent of like an active learning like setup to this might be useful. I had a follow-up question too. Since you have the generation and the perception, I was wondering if what you've worked on could be recast in an adversarial setup so that your system, for example, learn how to generate visual illusions, optical illusions, or as such. Do you think that that's a possibility? I think there are probably opportunities for detecting ambiguities and maybe even connecting it to how people perceive things, our biases about vision as well.
Yeah, I think that is really interesting. I haven't thought about it, to be honest. But yeah, so I started talking actually to some people from neuroscience about how the brain works and how we can tie it to neural networks. But we never talked about illusions. I think that's super interesting for sure.
Well,
Can I also ask a question?
Yeah.
Yeah, if you're done, Metin, sorry.
Yes.
Okay, so Cengiz, the first slide that you had shown at the beginning was like you were saying that if you know all the components of a virtual world, like cameras, light sources, and models, textures, and then you can learn a renderer, right? And then you can actually create realistic images, and you use this idea to some extent. But as far as I see, you use this idea in a kind of more simplistic settings, right? It's not like knowing all the parameters of the scene and generating the realistic image, but it's like the points in a point cloud, and based on that you actually create some renderings of isolated objects whatsoever. So do you use somehow a more, sophisticated, complicated setting for this so-called neural rendering, so that maybe, so that's also related to state of the art, maybe in this research area, which is important, I guess. That might also, if you can use real images to learn these realistic renderings, then you can use this neural rendering idea maybe for perception as well in a much more general settings. I don't know if I made myself clear a bit. So do you use, is there any cases where you can use this, or people use this, or this is something in progress, I guess, right, at the moment?
Exactly. It's actually now kind of a new subfield. Yeah, there are different approaches. So one thing, of course, you could use the classical standard path tracing algorithm to get this super realistic renderings. That's actually something we did recently. But it's pretty slow, and we tried to speed it up, but it's really not possible. After some optimizations, you cannot go too far. And then there's the alternative of neural rendering. So you say, for certain parts of my render, actually, I say I approximating it with some neural network, for example, for appearance. So I'm saying, okay, the geometry is there, But for each point on the geometry, I model the interaction of light with the geometry with a neural network. So it's like a smaller network, like a feed-forward one, for example, so that you can actually have an approximation of your global illumination. And this is something people are actually actively working on quite a bit these days, because it's fundamentally because of efficiency. If you would have really like a super computer where path tracing with billions of rays is really fast, then I think we wouldn't care too much. But yeah, at the moment, that's a big problem. And the other problem is biases or inductive biases that you introduce into the system. Sometimes they're not actually sufficient. So if you have super complex models, so for example, a full BSDF model for the material, a full like free-form geometry model in terms of a surface mesh, etc. That's basically, it's really hard for the algorithm to figure out, is it like a lamp, is it a hand? Should I have some specular highlight here or there? So then basically people say, okay, maybe some of these things I can explicitly model using neural networks or some other models. For example, I can have models for the geometry, I can have some fit models for the appearance, and basically use them for getting photorealistic renders that actually also allow this inverse process. So I mean, so the first problem is getting it super photorealistic, sometimes even having all the global illumination, for example, caustics, etc. And the second problem is still having the right inductive biases in your system such that the algorithm is not completely confused because you introduce so many degrees of freedom into the system.
Okay, thank you.
Okay, we're a few minutes over our time, so I'd like to thank Cengiz again for this thought-provoking talk. And I guess if you have follow-up questions, you have to catch him over email. So thanks again, and thank you everyone for joining us as well. Have a nice day, everyone.
Thank you very much for having me.
Thank you, Cengiz. It was a nice, great talk. Thank you.
Thank you, Cengiz.
Thank you very much.